So now we're going to dive a bit deeper into linear hyperbolic systems and see why the eigenvalues and eigenvectors are so important, and look at how we can use an understanding of the eigenvalues and eigenvectors to work out something about how the solution behaves, and also look eventually at boundary conditions. So again, we're looking at a linear hyperbolic system, first order system, qt plus aqx equals 0. To start with just the Cauchy problem, so it's on the entire real line. And M is a constant matrix. It's independent of x and t. And again, we say it's hyperbolic if A is diagonalizable with real eigenvalues. What that means is that there's a non-singular matrix R of eigenvectors that diagonalizes the matrix. So the similarity transformation R inverse AR transforms A into a diagonal matrix lambda with the eigenvalues on the diagonal. And the eigenvalues are the wave speeds that are important in the problem. And the eigenvectors, the columns of the matrix R, will also be very important because they tell us how to split arbitrary data up into a set of waves that propagate at different speeds, the eigenvector corresponding to each eigenvalue. And so we need this matrix of eigenvectors to be non-singular so that we can split up an arbitrary vector Q as a linear combination of its eigenvectors. So if we start with a very simple scalar equation, then qt plus uqx equals 0, again, is the simplest linear hyperbolic equation, the advection equation. U has to be a real number. It's a 1-by-1 matrix. It's certainly diagonalizable in that case. And with any given initial conditions q0, the solution is just q0 of x minus ut. It simply translates at speed u. And we can think of that as saying that the value of u, of the value of q rather, is constant along a certain set of curves in the xt plane called the characteristic curves. Functions x of t, capital X of t is x0 plus ut is a characteristic curve, a curve that looks like this on the bottom here, starting at some point x0 and propagating in time. So time is going upwards here. This is the x-axis over here. And from any particular point x0, if we solve the characteristic equation, we get xt is x0 plus ut. So it simply propagates along. This would be x0 plus ut. And this is drawn for a case where u is positive, so that the advection is to the right. If u were negative, then the characteristic curves would be going off in the other direction. And if you look at the solution along one of these curves, if we take q and evaluate it at some point x of t at time t, different points along the same curve, then you can easily calculate that if you differentiate that with respect to time as you move along this characteristic curve, you get dq dx times x prime plus dq dt, but that's exactly qx times u, the advection velocity, plus qt, and that, according to the differential equation, the advection equation is 0. So that says that q is constant along this characteristic curve. So for a scalar problem, it's very simple, but for a system of equations, it turns out we can sort of decompose things into this simple case along characteristic curves that are defined by the eigenvalues of the matrix A. So if we have a more general system, qt plus aqx equals 0, and it's hyperbolic in the sense that we've looked at, then that means that we have a matrix R of eigenvectors, so that A times the pth column of R is lambda p times the pth column of R. That's what it means for Rp to be an eigenvector. And if we put all of those columns of Rp eigenvectors together into the matrix R, then this says that A times the matrix R is simply equal to R times lambda. Notice the order is different here because if we scale each column vector by a different eigenvalue lambda, that corresponds to multiplying the matrix R on the right by the diagonal matrix lambda, this diagonal matrix containing the eigenvalues. So being diagonalizable means that we have a complete linearly independent set of eigenvectors, or that we can take the matrix A and apply a similarity transformation that turns it into a diagonal matrix. So if we look at a constant coefficient linear system and we have this non-singular matrix of eigenvectors, then we can take our system and simply multiply by R inverse. And if it's a constant coefficient system, then the matrix of eigenvectors R is constant, so is its inverse. So after we've multiplied by R inverse on the left, we can then also introduce R times R inverse, which is just the identity matrix, in between A and dq dx. And then, because R is constant, we can move R inverse inside the derivatives. So this R inverse times qt is the same as the time derivative of R inverse q, and R inverse qx is the x derivative of R inverse q. So if we introduce w as R inverse q, then what this equation says is that the time derivative of w plus, we now have here R inverse AR, which is exactly the diagonal matrix lambda, times R inverse QX, which is WX, equals 0. So again, that only works because we're looking at a constant coefficient system where the eigenvectors don't vary with space or time, so we can move them inside the time derivative and inside the x derivative. And so that allows us to take this linear system and diagonalize the system into Wt plus lambda Wx equals 0. And that's a system of m equations, but each equation is simply an advection equation. The pth component of W satisfies the equation time derivative of the pth component of W plus lambda p, the pth element on the diagonal matrix lambda, times the x derivative of the pth component of W equals 0. And so it decouples this linear system, which coupled all the components of Q together, into totally independent scalar advection equations, one for each component of the system. And we see that the eigenvalues then become the advection velocities. So those are the wave speeds of waves in our original linear system. And the WPs, the eigenvectors, are important. The R vectors are important. The W's are sort of the decomposition of Q into eigenvectors. So when we multiply here, W equals R inverse Q, that's telling us that we can then write R times W equals Q. In other words, W gives us the proper linear combination of the columns of R, which are just the eigenvectors, to take in order to get Q. So it decomposes Q as a linear combination of the eigenvectors, and then each of those eigencomponents simply propagates with speed lambda p, corresponding eigenvalue. So if we want to solve the general Cauchy problem with arbitrary initial data for all x, then one way we could do it is to take our initial data, multiply by R inverse, decomposing it into these characteristic variables, the W's, and then we know how to solve the advection equation for each component of W. Wp at xt is simply the initial condition W0, which came from R inverse times Q0, evaluated at x minus lambda pt. That's the solution of the pth advection equation propagating at speed lambda p. And then once we have all of these WPs, if we put them into a vector W and multiply that vector by R, that gives us back Q. Or think of these WPs as the coefficients of the eigenvectors R1 through Rp. These coefficients WP are varying with time now, but when we take that linear combination of fixed eigenvectors in R, that gives us Q at the corresponding time and space point. So we can also rewrite this as Q is a linear combination of these fixed eigenvectors Rp, where the Wp of xt is the characteristic variable at xt, and again by the fact that those satisfy advection equations, that's just Wp0, the initial value of Wp at x minus lambda pt. So this matrix vector product we can also think of as a sum of waves propagating at different speeds. So let's see how this applies to linear acoustics. So this is the system of equations for perturbations in pressure and velocity when we linearize about some constant state. And here I'll assume that the constant state has zero velocity that we're linearizing about, so it's gas at rest. But we have some small pressure perturbation perhaps initially, and then the perturbation satisfied this linear system of equations where k0 is some constant we saw comes out of the linearization, the bulk modulus, and rho 0 is our unperturbed density, and we end up with this hyperbolic system. And for this matrix, it's easy to compute the eigenvalues and eigenvectors. The eigenvalues, as we saw before, are simply plus or minus c0, where c0 is the speed of sound for this particular state that we're linearizing about. It's the square root of the bulk modulus divided by the density. But now we also see the eigenvectors r1 and r2, and these are two constant vectors. Again, they depend on what state we're linearizing about, but for a given r0 and then the corresponding c0, the two eigenvectors are minus rho 0 c01 and plus rho 0 c01. This product rho 0 times c0 is what we call the impedance, and again that depends on what state we're linearizing about, what the impedance is. You can also write that as the square root of k0 times rho 0. So the eigenvectors are, again, two fixed vectors. They're linearly independent, provided that rho 0 and c0 are both positive anyway. These two vectors are linearly independent. If rho 0, c0, the impedance was 0, then these would be the same vector and things would break down. We'll look at that case later. But in general, if we linearize about some non-zero density, then we would expect these eigenvectors to be linearly independent, and the eigenvalues are real numbers. So it's a hyperbolic system. And the eigenvalues, again, tell us the wave speeds, that tell us that acoustic waves propagate through a one-dimensional tube at speed plus or minus c, where c is the speed of sound in the gas. And again, if we've linearized about zero velocity, then there's no background flow, so it's just plus or minus c0. But the eigenvectors also tell us something. They tell us what the waves look like that are propagating with different speeds. So if we think of a simple wave, a pure one wave, a wave that's propagating along at speed lambda 1, with the variation proportional to the eigenvector r1, we call that a simple wave if it only involves one of these eigenvectors and eigenvalues. So we can approximate, or we can obtain such a wave by taking some fixed state and adding some function of x times r1. Don't add in any component of r2. Have the coefficient of r2 always be 0, so that we have the steady state that we're linearizing about. Sorry, I called it q bar again here rather than q0, but this would be the state we're linearizing about, plus some small perturbation that's only in the direction of r1 at every point x, maybe varying with x, but always in the direction of r1. Then the solution at xt is simply q bar plus that w1 propagating at speed lambda 1 times r1 at all times. Or if we look at what the variation of this is, the derivative with respect to q, or a small delta q, if we look at q at two nearby points, then that's proportional to this eigenvector. So the derivative of q, or if you just differentiate this, the derivative of q is really just the derivative of w01, again, times the same eigenvector r1. And so variations in this simple wave also are proportional to the same eigenvector. So if we're looking at a one wave, so it's all the variation is proportional to r1. R1 for acoustics is just the vector minus z01, or z0 is the impedance of the state that we're linearizing about. And so what this tells us is that any variation we have in pressure and velocity must be proportional to this eigenvector. So that means that in particular the variation in p has to be minus z0 times the variation in u. Px is always minus z0 times ux. And similarly, if we had a two-wave, a wave that's propagating, in this case, to the right with speed plus c0 rather than to the left with speed minus c0, then any variation in the pressure and velocity in that wave has to be proportional to the eigenvector r2, which is just z1 rather than minus z1. And so that tells us that in a right-going wave, the pressure variation is the impedance times the velocity variation. So if we start, for example, with initial data where there's some variation in the pressure and zero velocity, so say we have, for example, a Gaussian peak in the pressure and zero velocity. This is supposed to represent the two components. They're both varying around zero, but u is identically zero, p is initially some Gaussian. Then we could take that vector, p of x, whatever our variation p of x is, and zero, and decompose it as a linear combination of the two eigenvectors. And in this case, the linear combination that we take, it's easy to work out that for this particular choice, when u is equal to zero here, the linear combination that you have to take is simply minus p of x over 2z and plus p of x over 2z. Then when you add these two together, the velocity components cancel out, and the pressure components add up to p of x, whatever your p of x is. So this is our decomposition into the characteristic variable w1, which varies with x, however, depending on how p varies with x, times the eigenvector r1, plus the characteristic variable w2, also varying with x, it's p of x over 2z, times the eigenvector r2. And then if you want to look at what the solution is at later times, well, each of these is simply propagating with its corresponding eigenvalue, solving an advection equation. So you can think of this initial data as being sort of a linear combination of two waves, one of which has a pressure variation that's, well, when you multiply by z here, it's just p of x over 2, and the other one also has variation p of x over 2, but the two have different velocities, minus p of x over 2z and plus p of x over 2z. And as those propagate outwards, what you see is that they separate, and you can more clearly see the two eigenvectors. This is the eigenvector moving to the left here, which is moving with speed minus c. It has a pressure variation that's half the original peak, and a u variation that's negative relative to that. It's going to be minus p of x over 2z, and the wave moving to the right with speed plus c has the other half of the pressure variation and a variation in velocity that's positive, in this case p of x over 2z. And these two would simply move out. So this would be the solution of an acoustic problem where we start with, say, a small perturbation in pressure in the middle of the pipe, and then we let it go, and that's going to give you two acoustic waves that are moving out in opposite directions. And if it's initially zero velocity, then that initial pressure pulse is simply going to split into two and move in the two directions. As the pressure pulse propagates, the fluid is slightly accelerated and decelerated as that wave goes by, and so you have a variation in the velocity as the wave goes by, or a variation in the velocity that's moving along with the pressure variation. And the wave that's moving to the right is sort of pushing the fluid a bit to the right as it goes by, so we would expect that the velocity on the right is positive as the fluid moves a bit to the right as the wave goes by and then goes back to zero, whereas the wave moving to the left is moving the fluid a little bit to the left as it passes by, so we expect a negative velocity hump corresponding to the pressure hump that's moving to the left. But we can see that this relation between pressure and velocity and a left-moving wave and a right-moving wave is always given by the relation between the components, first and second components of the eigenvector r1 and the relation between the first and second components of the eigenvector r2. So this gives a really nice way to sort of decompose any data. Here we looked at special data where the initial velocity was 0, but you could take any data, initial variation in P, initial variation in U, and split it up into eigenvectors and see how that splits up into left-going and right-going acoustic waves. Another way to look at this is that we can define the characteristic curves just as we did for the advection equation. We can define characteristic curves for the acoustics equations and see that these characteristic components are constant along those characteristics, and therefore we can think about finding the solution at a general point by tracing back along a characteristic. So I've written here the solution to the acoustics equations again as a linear combination of R1 and R2 eigenvectors, where the characteristic components sorry, are given in terms of the eigenvalues minus C and plus C. If we take our initial data and split it up as take our initial Q rather, and split it up as a linear combination of the eigenvectors, that gives us the initial W. Another way to look at that is when you multiply by R inverse, you're multiplying Q by the first row of R inverse or the second row of R inverse in order to get W1 or W2. So you can also think of the W's as coming by multiplying the Q vector by rows of the R inverse matrix, which are left eigenvectors of the matrix Q. Sorry, left eigenvectors of the matrix A. Since if we multiply LP, any one of the rows of R inverse by A, what we get is simply that row vector multiplied by lambda P. And so when you put all of those together as rows of a matrix, we get again exactly the same equation we had written for the right eigenvectors. In that case, it was A times R is R lambda. Here it's R inverse times A is lambda R inverse. But it's the same similarity transformation in either case. And so if we look at a particular point, if we look now again at the xt plane, so time is going upwards here, x is our horizontal axis, and we look at some arbitrary point xt and we ask what's the solution of the acoustics equation at this particular point xt, then one way to think about it, we saw before that we could sort of split up the initial data and see its components that are propagating in different ways at different speeds and propagate them sort of forward in time and then add them up again. But you can also go sort of backwards in time from an arbitrary point. We can write the solution Q at this point as a linear combination of R1 and R2, and the coefficients are simply W1 evaluated at x minus lambda 1t, and in the case of acoustics, lambda 1 is minus C0, so that becomes x plus C0t, so that would be saying we take W1 back here at this point and look at the initial data at this point x and calculate, if we do the eigen decomposition of Q at this point, then we take the W1 component here, and that's the coefficient of R1 in our solution at this arbitrary point xt. And then if we trace the other characteristic back, and the other characteristic has lambda equals plus c, so when we trace it back, we're moving in the negative direction, going backwards in time, and so we can take the initial data at this point and decompose it into eigenvectors, and we would take the W2 component from here and the W1 component from here and use those as the linear combination in getting Q at this arbitrary point here. So that's another way of looking at it that will sometimes be useful, is to think about defining the solution at an arbitrary point by tracing back along these characteristics that the characteristic variables are constant along. So let's look at exactly that same example, but now this is just a slight variation where I'm assuming that we're linearizing about some u0 rather than about zero velocity. And we get exactly the same equations, except that there's a u0 on the diagonal now, if you remember from the linearization we looked at. And so we now need to look at the eigenvalues and eigenvectors of this matrix. Well, it turns out the eigenvectors are exactly the same as they are in the case u equals 0. But what changes is the eigenvectors are shifted by the value u0. And that's easy to see because this matrix A we can look at as being u0 times the identity matrix plus the coefficient matrix for the previous case, acoustics about 0 velocity. And when we split up a matrix, or if we take a matrix and add a constant times a diagonal matrix, then that constant times a diagonal shifts the eigenvectors by that constant value. Shifts the eigenvalues by that constant value, but it leaves the eigenvectors alone because these eigenvectors, they're eigenvectors of this matrix, but they're also eigenvectors of the identity matrix, since any vector is an eigenvector of the identity matrix. So if you multiply A times one of these vectors, you'll easily see that you get just the corresponding lambda times that same vector again. So the eigenvectors are independent of u0. It's only the eigenvalues that get shifted, and they get shifted in exactly the way we expect, that if you're linearizing about gas that's moving at some constant speed u0, then the sound waves are moving relative to that gas speed. So, oh yeah, maybe I should draw maybe one picture here that sort of illustrates that. So if we have the speed, say this is some x0 plus u times t is the speed at which gas is moving along, then the eigenvectors would be the same as before, but the eigenvalues, being u minus c and u plus c, would correspond to waves that are moving slower or faster than this by the speed of sound, c0. But you could do the same sort of thing also tracing back along characteristics. It's just that you have characteristics now that are moving at speed plus or minus c0 relative to the gas velocity. Okay, so let's shift gears a little bit and look at the initial boundary value problem. So far, we've only looked at the Cauchy problem, where we were looking at the entire real line as our domain. And so we didn't have to worry about boundaries. We assumed we had initial data defined everywhere, and it simply shifts forever at speeds given by the eigenvalues. But what happens if we look on a finite domain? So we're now looking only on some interval, x between a and b, say, for positive time. And we have some initial data, which I guess I've changed notation a bit here, and I'm calling it eta of x rather than q0 of x. It's eta of x is our initial data. And we also have, turns out, we will have to have some boundary conditions, as you would expect. If the flow is to the right, if u is positive, and then things are flowing in at the left boundary at x equals a. And so if u is positive, we have to know what's flowing in at that boundary. And if u is negative, on the other hand, we have to know what's flowing in at the right boundary. So we need some boundary condition. We need some function g of t, but we don't need it at both boundaries. We only need it at the boundary where things are flowing in. And so if you look at it in terms of the characteristics in the plane, these are the sort of the characteristics that are moving. Again, this is the xt plane here. So this is our interval from a to b. And we've got initial conditions that would have to be specified everywhere on the interval as usual. But in addition, if flow is to the right, if u is positive, then flow is along these characteristics in this direction. And so in addition to needing data along the boundary, we also need data along x equals a. That determines the value along these characteristics that are coming into the domain from the left boundary. And you can write out the solution in terms of your function eta of x, the initial conditions down here, and your function g of t that's specified along the left boundary in this form. You can also see that sort of at any point you can trace back a characteristic, and it either hits the initial data or it hits the boundary, and then we can use the advection equation solution to work that out. There's another set of boundary conditions that's sometimes useful to look at in some situations, which are called periodic boundary conditions. And this is a sort of different boundary condition. This boundary condition says that Q at AT is always equal to Q at BT. So whatever we have at A is equal to what we have at B. So this might be the situation if we looked at advection not in a straight pipe, but rather in a circular pipe, flow that's going around in a circle. And suppose we can still model it with one-dimensional equations. So it's basically behaving one-dimensionally. There's a velocity in the azimuthal direction as it goes around this circular pipe. But if we want to model this as an advection equation, we get the same equation as before if we think of x now as being distance along this pipe, but we have to introduce some arbitrary point where we sort of cut it off, and then we let a maybe be here and x be distance around this pipe until we get back to the other end. And so in that case, a and b sort of represent the same point in this pipe, but when we spread it out as a one-dimensional problem, a and b would be the two boundaries. But now what we have is that anything that flows out the right boundary simply flows right back in on the left boundary. And so values flowing out at one end have to come in the other end, and that can be expressed as this periodic boundary condition. So computationally, periodic boundary conditions are often quite nice to work with because you don't have to worry about exactly how many boundary conditions we need at each side. You just set Q at one side equal to Q at the other side, and that can work more generally if we had, for example, gas in a tube that was connected like this, a circular tube. If you were looking at gas dynamics in the tube, you could also look at periodic boundary conditions in the same way. But more generally for acoustics or for gas dynamics, if you're not looking at periodic boundary conditions, then to figure out what sort of boundary conditions we need, it's useful again to look at these characteristic variables and the Eigen values and eigenvectors of the matrix. And so if we take our domain and cut it off now at some point, so we put a boundary here at x equals a and another boundary at x equals b, then we still have this family of characteristics moving to the right and to the left everywhere. But what we see is that if we look at an arbitrary point, say we look at this point, well, we can trace back one of the characteristics to this point and the other characteristic to here, and we can calculate the solution at that particular point exactly in terms of the initial conditions at 2 points. On the other hand, if we took a point, say, here, instead, then tracing back this characteristic, we would evaluate our W1 characteristic value at this point from the initial data, but when we trace back this characteristic, we hit the boundary. And so in this case, we would need to get the W2 characteristic coming from this point on the boundary. Okay. But you can see from this picture sort of that all of these blue characteristics that are going to the right, those are the ones that correspond to W2, those characteristics are all coming from the left boundary and going into the domain. And so for those characteristics, we need to specify a boundary condition at the left side. So we need to specify W2 over here at the left boundary. It's this value. Whereas at the right side, it's the red characteristics that are coming in inward. Those are the characteristics that are carrying the information that's moving along the one waves. And so at the right boundary, it's W1 that we need to specify. So for the acoustics equations, we always have one positive eigenvalue, one negative eigenvalue. We have a system of two equations, but we need one boundary condition at the left and one boundary condition at the right. For a more general system, you can kind of guess what would happen. I think if you have a system of m equations with some number of positive eigenvalues and some number of negative eigenvalues, then you can tell from this characteristic decomposition exactly how many boundary conditions you need at the left and how many you need at the right. You need one for each incoming characteristic. So the number of positive eigenvalues tells you how many boundary conditions you need at the left. The number of negative eigenvalues tells you how many boundary conditions you need at the right. It doesn't tell you exactly what boundary conditions will work and what won't. You also have to make sure that your boundary conditions are actually specifying sort of the incoming characteristic. it wouldn't do to specify boundary conditions that only told you what W1 is at the left boundary, because W1 is determined entirely by what's flowing out from the inside. So you have to specify boundary conditions that tell you what W2 is at the left boundary, possibly in terms of the W1 that's flowing out, but you have to be specifying W2 properly. So we can look at a couple of examples of this. So one sort of boundary condition that's often useful computationally is what we call outflow boundary conditions, or non-reflecting or absorbing boundary conditions, where one of these boundaries, or both of them perhaps, are really just sort of the end of our computational domain, but not really the end of the problem. And so what we expect is that if we have flow going out this domain, it just keeps going out. Or if we have an acoustic wave that's going out this domain, it should just keep going out, and it shouldn't generate anything coming in. So there should be no incoming waves at the right boundary. So at the right boundary, we want W1, the incoming characteristic variable, to be 0, so that there's no waves coming in from the right boundary. There might be waves going to the right from the initial data, but from the right boundary, these waves all have strength 0. And similarly, coming in at the left boundary, if we have an outflow boundary condition here, we want whatever's flowing out along the 1 characteristics to simply leave the domain. We don't want anything to flow back in, so we could just set W2 equal to 0. So these boundary conditions are not specified in terms of pressure and velocity. They're specified in terms of the characteristic variables. So if you're working computationally, you have to make sure that you can translate these sort of boundary conditions into boundary conditions for the quantities that we're actually solving for, which we'll look at later. Another possible set of boundary conditions we've already seen are the periodic boundary conditions. If we just thought of acoustics in a pipe that's bent into a ring so that sound waves can just keep going around and around and around in the ring, we could split it up at any arbitrary point, and then any sound wave that hits the right boundary simply continues from the left boundary, and vice versa. And so in terms of characteristic variables, what that's saying is that the W2 variable at the point A, which is what's being transported along this characteristic, should be given by W2 at B at the same time. So at some time t, whatever is flowing out here on the 2 characteristic should also be what flows in here. And so we're specifying the inflow boundary at one boundary in terms of the outflow characteristic at the other boundary, which seems like kind of a strange boundary condition, but that's what you would have to do if you were doing this in terms of characteristic variables. Similarly, the W1 variable, which is the left-going flow at the right boundary, is just given by W1 at the left boundary. So what flows out here flows back in at the other boundary. But computationally, it's much easier and works just fine in this case to set Q of AT equal to Q of BT as the boundary condition. And again, when we start talking about numerical methods, we'll look at how to implement some of these boundary conditions. Now, another boundary condition that often comes up in this sort of problem is a more physical boundary condition of a solid wall or reflecting boundary. So if we have a pipe, but the pipe has an endpoint, there's a solid wall here, then we have a condition at the solid wall, since u represents the velocity in the x direction. At this solid wall at x equals a, there shouldn't be any motion in the x direction. If it's a solid wall, the gas can't go in or out at that boundary. So the boundary condition at a solid wall is that u at that boundary is equal to 0. Or if we put a solid wall also at b, then we would have a boundary condition that at the right boundary, u is equal to 0. So these boundary conditions are not really written in terms of the characteristic variables, but they're written in terms of what makes physical sense. But you can translate them into the characteristic variables. It turns out u equals 0 corresponds to saying that W2 is the negative of W1, because in general, remember, we can decompose Q as some W1 times the R1 eigenvector plus W2 times the R2 eigenvector. And if you just add those together, the velocity component is simply W1 times 1 plus W2 times 1 is just W1 plus W2. So if we want the velocity to be 0, we can just make sure that W1 plus W2 is 0. And that's what we accomplish with this sort of boundary condition. If we say W2 is minus W1, then we're saying that the sum of the two should be 0. In other words, the velocity should be 0. But you can think of this now in terms of the characteristic variables as saying that whatever hits the boundary and is given by W1 times R1 propagating to the left, at that time we have correspondingly an incoming variable W2 that's not the same as W1, but it's the negative of that in order to get velocity equal to 0. And so we get a reflected wave. It has now a different wave speed. It's moving to the right instead of the left. It has a different eigenvector, and it has a different coefficient because we negated it as it reflects off the boundary. So there's an example of this in the Clawpack gallery that comes along with the software on the web, which illustrates this and kind of animates figure 3.1 in the book. So let me pull up the gallery. And there's actually a number of things in here that might be of interest, but if we go down to the gallery of FVM book applications, this has some simulations that go along with figures in the book. And under chapter 3, there's 1D acoustics simple waves. There's a README file that has the equations here. And then if you go to the plots directory, there's plots of the solution at many different times. But this JS Movies shows you an animation created by putting all these plots together. And so I'll just show this animation to illustrate the solution of the acoustics equation with different boundary conditions. So this is actually showing a numerical simulation that was calculated on very fine grid with appropriate boundary conditions, and the ones that were implemented here was a solid boundary wall, a solid boundary condition or a solid wall at the left boundary, and an outflow boundary condition at the right boundary. And we'll talk later about how those are implemented in the numerical methods. But let's just take a look at how the solution evolves. So the top plot here is the pressure as a function of space at time 0. This plot is the velocity at time 0, which was initially taken to be 0, and I just took some funky sort of pressure perturbation so that you could easily see how it splits into two parts and moves to the left and the right. And remember, when we start with 0 velocity in the acoustics equations and any arbitrary pressure disturbance, what we get is the pressure splits into two equal parts, one moving to the right with positive velocity, both positive wave speed and also the velocity is a positive multiple of the pressure. The wave moving to the left is moving with negative wave speed, but also the velocity is the negative of the pressure times some multiple depending on the impedance. So if we let this go forward in time, just step through a few steps, then we see this splitting up of the initial pulse into the right going wave here and the left going wave here. And as this evolves, the left going wave is going to hit a boundary. The right going wave hits an outflow boundary where it's allowed to simply pass out of the domain without producing any reflection. The left going wave, on the other hand, when it hits the left boundary, will get reflected. And what you'll see is it comes back in with sort of the order of these humps reversed. But also as it comes back in, it starts moving to the right. The velocity will also be a positive multiple of pressure rather than this negative multiple of pressure we see in the left going wave. So as it reflects off the boundary, it's a little complicated, but then eventually we get this right going wave coming back in. So we can go back and watch the whole thing, slow it down a little bit here, watch how it evolves.